This class, Considering God's Works, is part of a larger grant program that is here at Berkeley Covenant Church, and it's a program funded by an initiative called Scientists and Congregations, and that's a program funded by the John Templeton Foundation. So you might be asking, well, what do we mean by God's works here, or why should we consider them? By God's works, I'm talking about the created world, the world of nature, the physical universe, our physical bodies, the stars, the heavens, as Scripture calls them, and pretty much the things God created. So why should we look at the things God created? Well, the most compelling reason is because the Bible tells us to look at that which God created, to study the things that God made. For instance, in Psalm 19, we read that we can know something about God by looking at what God has made. Psalm 19 says, "The heavens declare the glory of God, and the skies proclaim the work of his hands." So we can see something of God's glory by looking into the heavens, by looking into the skies. Psalm 8 also says, "You have set your glory in the heavens, the work of your fingers, the moon and the stars which you have set in place." Beyond that, there's Romans 1:20, which says we can even know more about God by studying the creation. And we read there, "Since the creation of the world, God's invisible qualities, his eternal power, and divine nature have been clearly seen, being understood from what has been made." And so we can understand something of God's very nature by looking at creation. And so there's many other verses like that. If you want a list of them, I included a few more in the introductory paragraph of the syllabus. But the point is that Scripture tells us that if we look at what God has made, we can actually understand something about God. And that's a pretty monumental thing if you let it sit with you for a minute. So what sort of questions will we be asking in this class? Well, for one, we'll be asking some questions about the present, like, is the Christian faith anti-science? Are Christians opposed to science? We'll be asking historical questions, such as, was this the case historically? Has Christianity always been anti-science, if that is the case? And what kind of creatures are human beings? What does it mean to be human when you look at both theology and when you look at both science? Is belief in the Bible incompatible with accepting that humans evolved from a common ancestor shared with other animals? And this is a more controversial question for many of us as evangelicals in the church today. Also, does belief in miracles conflict with the law-governed world revealed by the physical sciences? And so we'll be looking at the question, can God act in nature? And is this contrary to contemporary science? We'll also be asking some questions about human origins. Questions like, did Adam and Eve really exist? Was there really a first human pair? Is God responsible for natural disasters? When Hurricane Katrina hit and when the tsunami hit Southeast Asia a few years ago, was this God's fault? When we have diseases like AIDS and cancer, is God ultimately responsible for these diseases? So we'll be asking those kind of questions. And how do we understand the soul in light of neuroscience? We know so much about the brain and what the brain does, but where does that leave us with regard to the soul? And also, does science make the Bible and the Christian faith irrelevant? A lot of people you talk to, in Berkeley especially, will say, well, science shows that the Christian faith is outmoded and useless. So is this true? And what's the role of the Christian faith in science today? But today we're going to be asking the question, what is science? Right? If we're going to have a conversation between theology and the natural sciences, or between Christian belief and science, we need to understand first, what is science? What is this thing we call science? And we're going to be approaching this question from an academic discipline called the philosophy of science. And this is a discipline I studied in my PhD work, and so I'm trying to not be too specialized in today's lecture. I apologize ahead of time if some of the material is a little bit philosophical, but every class won't be like that, so be assured in that. But try to follow along with me, and hopefully we'll have some time to discuss after the class. For the sake of the film, we're going to save questions to the end of the class. So if you have a pen and paper and there's something on your mind, jot it down, and we'll talk about that after class. So what is science? Well, when we're asking that question, we're really asking, what is the truth status of scientific theories? What is their hold on reality? Do they really say something about the real world, or are they saying something else entirely different? So we're really asking the question of truth here when we ask about science. And it's also a question of how do we know what we know? And this is a field of philosophy called epistemology. You don't really need to remember that word, but I might say the word epistemic sometimes without thinking. And so you know, when I say that, I mean it's the question of how do we know what we know? So what is science? Well, what does the word science mean? It comes from the Latin root, and it's a word which means knowledge. Originally, science was much more broad than what we think of today when we talk about science. Originally, science, which was discussed by a philosopher named Aristotle, who lived about 300 years before Christ. He used the word episteme, and if you remember the word epistemology from the previous slide, episteme is the root of that. That also means knowledge. But he talked about science as any reliable body of knowledge that can be logically and rationally explained. And so, even today, we have this concept, this broader concept of science, like we talk about the social sciences and the political sciences. And so there's still that concept of a broader idea of science as anything that's rationally explained. But usually when we talk about science today, we don't mean that. We don't mean political science when you say you're a scientist. You don't really mean you're a political scientist. You mean you're someone who studies the natural world through experimentation, through observation. And this was actually an idea, this idea of scientist was coined by an English polymath who was a scientist and many other things, named William Whewell in 1833. And the idea of science, as referring only to the natural sciences, comes from the 1850s, and that's when that really came into common usage. So it's more of a modern thing to talk about science as only the natural sciences. Before that, the natural sciences were referred to as natural philosophy. Sometimes called the natural sciences, but mainly called natural philosophy. So people like Isaac Newton and Robert Boyle and early scientists they called themselves natural philosophers. So what is natural philosophy? Well, in medieval universities, this was the study of change and motion in the physical world. And this was the most widely taught discipline at all the medieval universities. For virtually 1,000 years, all students who obtained the Master's of Arts degree had studied natural philosophy. And so the study of nature was something that held a key place in the medieval universities starting over 1,000 years ago. It was also called the mother of all sciences because it was so comprehensive, because you were looking at the whole created world. The natural sciences, or natural philosophy, was called the mother of all sciences. Natural philosophy offered causal explanations for the chief features of the natural world. They asked the question, why? Why does the sun move? Why does the earth move? Does the earth move? Things like that. One of the most well-known natural philosophers, born in the late 1200s, was a guy by the name of John Buridan. Now, Buridan was a professor at the University of Paris, and as I said, he was one of the most important philosophers in the Middle Ages. Buridan studied things like earthquakes, what causes earthquakes, what's the nature of mountain formation, and most importantly, he looked into the issue of relative motion. Now, what's interesting about Buridan is when looking at relative motion, he said, well, it appears to us that the earth on which we stand is at rest, and that the sun moves around us. But he argued the reverse might actually be true, and this is in the early 1300s. He said, the observed celestial phenomenon would be exactly the same whether the Earth was moving or the sun was moving. If the Earth did actually rotate, we would be unaware of its motion. The situation would be analogous to that of a person on a moving ship that passes another ship that's actually at rest. If the observer on the moving ship would imagine himself or herself at rest, the ship that was actually at rest would appear to be in motion. Similarly, said Buridan, if the sun were truly at rest and the Earth rotated, we would perceive the opposite. On strictly astronomical grounds, Buridan argued, either hypothesis was supported by the celestial phenomenon. Now keep in mind, he was one of the most popular natural philosophers of the early Middle Ages. And so this issue of relative motion, does the Earth go around the sun or does the sun go around the Earth, was a live question long before Galileo. That's why I bring up Buridan, because we often have an understanding of the history of science that is kind of leaves out the Middle Ages and all the discussions of the Middle Ages. And all of a sudden you have Galileo, and there's the beginning of science. But that wasn't the case. There were some really key questions and investigations that happened hundreds of years before Galileo. But in the present, we talk about science in a different way. There's continuity with the ancient understanding of science, but we have in mind a very particular thing when we talk about science. Again, science itself means knowledge, but what kind of knowledge are we talking about when we talk about science? Well, we usually mean rational knowledge, knowledge that is that's gained rationally, knowledge that is observable, you can see it, not something like poetry or something like that. Facts. We say that science talks about facts, not values. That science is objective as opposed to subjective. That science is empirical, that you need to be able to see it out there in the natural world. If it's scientific knowledge, it has to be somewhere observable in the natural world. Science is often talked about as quantifiable and as testable. So as a working definition of science, I'll say that science is a project whose goal is to obtain empirical knowledge of the natural world. If you're not familiar with philosophy of science is a reflection on the nature of scientific theories and scientific practice. Philosophy of science examines science's internal structure, its components, its techniques, its assumptions, its limitations, and so on. Philosophy of science we can think about as the process of thinking rationally about what science actually is. And so that's the perspective we're going to be taking today. It includes science, but it's beyond science in the sense that you're asking the question, what is science historically and today? So historically, the traditional view of science was that scientific theories and laws were things that could be conclusively confirmed and conclusively falsified based on objective data alone, pretty much. This is a view that goes back to this fellow here, Sir Francis Bacon, who was born in the mid-1500s. He said that observation is the defining mark of scientific practice. And he said the act of observing phenomena should be followed by what he called inductive inferences to general laws that describe the data of observation. And so you make these general inferences when you look at things around the world, you make inferences and you come up with natural laws. However, there are some problems with the inductive approach, some logical problems. One is that it's not really possible to logically or validly move from a finite number of observations to the formation of universal laws. The other problem is observations are not made in a conceptual vacuum, right? You have ideas behind the very observations you're making, ideas about what are you looking at. Let me use an example here. So say we're observing the natural world, and you're looking up on a clear night, and the moon happens to be out, and you can see some stars. Say you're in the country somewhere where you can actually see stars. So you say, well, what do you see when you look up in this night sky? You might say, well, I see the moon and I see the stars. But what do you actually observe? What do you actually observe? You might see a lot of small, bright lights and then a whitish, larger, circular object. If you had never learned any science at all, what would you think this white object was? Think about it for a second. You're looking up in the sky, you see these little lights and a big light. If you knew no science, what would you think this object was? Would you think it was a flat disk? Or perhaps a sphere? Maybe you knew something about the Earth. Maybe you went around the Earth you circumnavigated the globe. So you might think, well, maybe it's an object like the Earth. But then you might ask, why do we always see the same side of it? Why does its shape change from a thin crescent to a full disk and then back again? You might wonder if people live there. Or you might ask, why does it move? Why does this object in the sky move? Could it possibly be alive? Could this be an intelligent being? And that was an answer that some people gave. Aristotle thought the moon was an intelligent being, right? And so did others. Other people thought the moon was a sort of god. But if you ask these questions without any science, you come up with very different answers. If you know some science, you might know that the moon is a large spherical rocky satellite that orbits Earth, made mostly of anorthosite crust, which is very silicate-rich. You may know that it's a quarter of the diameter of the Earth and 1/80th of its mass, or that it rotates once on its own axis at the same time as the Earth in what's called a synchronous orbit. You may know that the phases are due to the relative positions of the Sun, Earth, and the Moon. And you may even know that the curvature of space-time, or what we usually call gravitational force, caused by the Earth helps explain the regular motions of the Moon. You may know this, and you may know a lot more about the Moon. But however much of this you know about the Moon, you did not find it out by direct observation. You were told it. You possibly learned it from your parents, or a science teacher, or a documentary on the History Channel. And even professional astronomers will generally not have checked the truth of any of these statements by their own empirical observations. So how do they get to these conclusions? Well, they rely on the amassed authoritative observations and the theoretical reasonings, the logical conclusions of the scientific community, which over a period of many centuries have established these facts as fundamental physical truths. And so this is a long process. To know what we know about the moon is a process that goes back hundreds of years in terms of observation, in terms of testing. But by and large, even scientists who study the moon will not have been to the moon to check these things, or will not have done a lot of the observations themselves. We don't start from scratch in science. You continue from what has begun. Isaac Newton says, if I have seen farther than others, it's because I've stood on the shoulders of giants, right? Talking about his scientific insight. Einstein quoted Isaac Newton and said the same thing. That quote's often attributed to Einstein, but it was actually Isaac Newton who was saying that several hundred years before Einstein. But that's the nature of science, is there's a history in science. So while it's true that scientific knowledge is based on tested against observations of the natural world, there's much more than just pointing one's sense organs in the right direction. Also, one cannot possibly record everything that one observes. It's just not humanly possible. Some sort of selection is needed, and thus observation is always selected. You choose what you're going to observe, what you find interesting. What is an interesting phenomenon that you decide to observe? These are the sort of questions that go into observation. There's also a key role for presuppositions in science. Presuppositions that are absolutely vital to practice of science. To generalize the data into physical laws, the individual scientist must assume that the laws apply for physical processes that are not observed. For example, the uniform operation of nature is observed when we make observations, when we study physics and we say, well, Einstein's laws of general relativity apply across the universe. We have not been across the universe to see whether or not these apply. We have not done experiments in other solar systems to see if that's true. But we assume that there is this uniformity of nature. We'll talk about the historical roots of these assumptions in a couple more classes. But for now, it should be sufficient to realize that even though scientists have actually not tested the laws that they accept everywhere, They assume that these laws apply throughout the universe. And then there's the issue of unobservable phenomena. Right? There are things that we don't directly observe, such as forces and fields, genes and subatomic particles. We don't see these directly. Sometimes we can see things that we interpret their presence through instruments, like the ones pictured here. That's the one on the image on the upper part of that is the study of the Higgs boson, if you've been following that at all. But there's an inference there about what's going on. You don't actually look at matter and see the Higgs boson with your naked eyes. And so there's a lot that goes on through trusting instruments. But then there's also theoretical entities that we can't even observe directly, but we think exist. For instance, again, the Higgs boson is a theoretical entity that scientists are looking for. And then there's things like genes, which there's many different definitions of what we call a gene, but scientists are sure that it exists out there somewhere. And so there's all kinds of theoretical entities that scientists accept, but again, the traditional understanding of science does not allow place for unobservable entities. Other problems with the inductive approach. Theories are underdetermined by the data. So what do I mean by underdetermined? Well, many competing theories can be consistent with the same set of data. Data by itself cannot exclusively confirm one theory from among its empirically indistinguishable competitors. And as an example here, I have Tycho Brahe's understanding of the solar system, which was different from that of Copernicus. Now, interestingly, Brahe and Copernicus each had a competing theory of the solar system, and it can be shown mathematically, and according to the observations of the day, what was available to them, even at the time of Galileo, that every bit of data that is predicted by one theory would be predicted by the other theory. So these two theories, that of Tycho Brahe and Copernicus, were indistinguishable for hundreds of years, based on empirical data. And if you don't know Tycho Brahe's understanding of the solar system, there's the sun, there's the earth, the sun goes around the earth, and the moon goes around the earth, but everything else, Venus, Jupiter, Mars, and so on, go around the sun. And so it's sort of a halfway between what was called the Ptolemaic system, where everything went around the earth, and the Copernican system, where everything went around the sun. But the data did not allow you to distinguish between Copernicus and what's called the Tychonian system. So I think actually the 1800s, but we'll talk about that in a little bit. Other problems with the inductive approach. There is no known rigorous inductive logic that can infer unobservable theories and concepts solely from the data that they intend to explain. The conclusion of all this is that if Francis Bacon was correct, and if the inductive method is the correct scientific method, then the majority of theories that we currently accept as science are not actually legitimate science. This becomes very important when you start reading the literature of young Earth creations. Okay? If you look at how most young Earth creationists, like Ken Ham, will explain science, they explain science through the inductive approach. This idea that you need to actually be able to observe everything, and that you need to be able to come up with general laws and conclusions based on your observations. But if you take this idea strictly, atomic physics would not be part of science. Most of cosmology would not be part of science. And so you might get rid of evolution. You might get rid of the science of the evolution of life, but you actually get rid of most other sciences we know today. So one person who realized this and wrote on this, starting in the 1930s, was a guy by the name of Sir Karl Popper. He was a philosopher of science, and he argued that rather than focusing on verification in science, we should focus on falsification. in order to talk about how scientific progress happens. For instance, it only takes one sighting of a black swan to falsify the hypothesis that all swans are white. And this idea of Popper's reverses the way in which scientific rationality was traditionally thought of. Rather than moving inductively from observations to generalizations, which was the original way, Popper suggests that we proceed by deducing predictions from the available theories, which theories are out there. Let's make predictions from those theories, and then test them with a view to the possible refutation of the theory in question. And so rather than moving from observations to generalizations to theory, Popper says we do the reverse. We start with theory. We say, what predictions does a given theory make about the world? And then we try as hard as we can to refute those theories. And the refuted theories we know are not true. That means that the defining mark of scientific practice becomes falsification. And this has been a very influential view. It's a view that most practicing scientists will hold, according to surveys of scientists in the field. So this idea of you're trying to falsify a given theory. And science then involves formulating novel hypotheses and trying to prove them wrong. Again, the focus here is that scientific hypotheses, in order to be scientific, must make testable predictions about the world that can be potentially falsified by later experimentation or observation. If something is unfalsifiable in principle, it's called pseudoscience. And it's the difference here between astrology, which is in this picture, and astronomy. Right? There's no way you can falsify the predictions of astrology. They're set up in such a way that they're very vague. They don't make testable predictions. And Karl Popper would also use Freudian psychology as an example of pseudoscience, because it's in principle unfalsifiable, and he talked about Marxism as unfalsifiable in principle. So the idea that there aren't any predictions that these theories make, which can actually be falsified by data. But just because something's falsified doesn't mean it's pseudoscience, and that's important to keep in mind. The Tomek model here, which was the idea of the cosmos that came from Aristotle and this guy named Ptolemy that was the most influential throughout the early Middle Ages. This was actually science, right? By the time Galileo came along, after much discussion and observation, it eventually became falsified science. But the Tomek model made predictions that could be falsified about the world. And so it's important to keep in mind the difference between science which can be falsified and pseudoscience. And falsificationism, as we understand science today, does not allow us to say that today's scientific theories are actually true or even probably true. So we ask about, well, what is the truth status of these theories? We can't say that theories are true. The best we can say about any given scientific theory today is we have not been able to falsify it yet. That's the truth status of any given scientific theory today. And we'll talk a little bit more about that. However, don't pitch your tent just yet. There are some doubts about the received view that have emerged starting in the 1950s. There's some questions even about whether this view accurately describes what scientific practice is and how science happens. Philosophers and scientific theorists realize that all data is theory-laden, and you already have theory assumptions within the data itself. So scientists are not so much engaged in seeing the world as it is, but seeing it as something in particular. I might say, see if you can find the chalice in this image, and you're looking for a chalice. You might miss that there's two faces instead, which I could ask you to look for. So this idea that when we're looking for something in particular, it's very difficult to get theory away from the actual looking at the data. One philosopher of science and physicist by the name of Ian Barber says, "There are no bare, uninterpreted data. Expectations and conceptual commitments influence perceptions, both in everyday life and in science. Human individuals supply the categories of interpretation right from the start. The very language in which observations are recorded is influenced by prior theories. The predicates we use in describing the world and the categories with which we classify events depend on the kinds of regularities we anticipate. It is not possible in the everyday practice of science to separate theory from observation. And no amount of experience and observation can conclusively falsify a given theory. So even theories that might seem falsified are not conclusively falsified, right? And a good example is a guy by the name of August Weismann, who was a biologist in the late 1800s who was trying to prove a guy named Lamarck wrong about evolution. And what he did is he cut off the tails of 5 generations of mice to see whether the next generation would inherit the acquired characteristics of the generations before. And this was seen at the time as a somewhat definitive refutation of the idea that acquired characteristics can be inherited. The idea that if you work out enough and get lots of muscles, your children will get those muscles. Or if you have a healthy diet, your children will be also healthy eaters. Things like that. And so he said, no, that's not the way inheritance works. And he did experiments to prove this. And these were seen for many generations as definitive. What's interesting is now there's a field of biology called epigenetics that is showing that some characteristics, not as Lamarck thought of them, but our habits and our environment might be passed on to our offspring. So that's now an open question. So Weismann's experiments were not conclusive. They did not conclusively falsify Lamarck for the rest of eternity. So there's always open questions in science. The other thing is that popular theories are resilient to falsification in the face of scientific anomalies. And that's the point of this cartoon here. If any of you have been following the scientific news, you might have seen experiments which seem to indicate that little particles called neutrinos go faster than the speed of light. And that is a problem for Einstein's theory of relativity, which says that they shouldn't go faster than the speed of light. But even if that experiment turns out to be accurate, you're not going to have every scientist automatically rejecting Einstein's theory of relativity. That's not how science actually works. People hold on to theories even if there's a key experiment which seems to refute the theory. So theories are actually more resilient than one experiment, right, which seems to falsify those theories. So to address some of these problems, a philosopher of science and historian of science by the name of Thomas Kuhn talked about some of this stuff in his book, The Structure of Scientific Revolutions. Even if you don't know Kuhn, you know one of the words that he coined, which is paradigm and paradigm shift. He was the first person to talk about paradigm shifts, so you could thank him for that. He says that science consists of multiple paradigms, each of which is composed of a network of commitments and a set of approaches and problems. The paradigm determines for the scientist what there is in the world, what actually exists in the world, the sort of questions that you're able to ask. And it tells the scientist what he or she is seeing when recording observations. Kuhn says that different paradigms represent different worlds with no overarching perspective for comparing them. And he calls this incommensurable, that two paradigms are like two different universes, and you can't just leisurely move from one to the other. Rather, what Kuhn sees in the history of science is long periods of what he calls normal science, where scientists are working within an established paradigm. And then, through experimentation, you'll see the slow rise of anomalies, and people pretty much ignoring those anomalies at first. Then scientists, when there's enough anomalies, will start to have misgivings about the established paradigm, but they won't really do anything in particular because there might not be a new paradigm to go to. But then when an attractive alternative paradigm arises, a scientific revolution, which is a radical shift from the old paradigm to the new one, may occur. And so this, in his study of the history of science, this is what he sees as typical in the history of science, this sort of process. However, scientific revolutions are not logical or rationally determined, but he says they look more like religious conversions in which one scientist seeks to convert others to his or her way of seeing. And he talks about propaganda wars, and you're really trying to convince other people. And he said it looks quasi-religious rather than a sort of logical movement from one paradigm to another. That's the idea of the shift, is sort of a radical shift. He says the shift is like a Gestalt switch and must occur all at once or not at all. And it's sort of, the idea of a Gestalt switch is you either see the old woman in this picture, or you see the young woman. You try to see both of them at once, and it really doesn't work too well. Whereas with the chalice, you can see two people kissing the chalice. It doesn't work as well. Another philosopher of science who went a bit beyond Kuhn in his understanding of science is a guy by the name of Paul Feyerabend. He wrote a book called Against Method, and he was really looking at the role of aesthetic judgments and values in the actual practice of science. That science was dominated by things like taste and subjective wishes, interests of particular individuals. And so he documented a lot of interesting cases of particular scientists who he said were more value-driven than driven by other things. So he came to the conclusion that there is no longer any distinction between science and art. And so Feyerabend's sort of on the one side of the issue. Your practicing scientists would sort of be on the other side of that spectrum, right? But the hotly debated question with regard to scientific truth is this. If the objective picture of scientific activity and theories is untenable, if we can't say that we have absolute objectivity in science, then how far towards the subjective end of the continuum should we place the scientific project? Should we agree with Feyerabend that science is no different than art? I think intuitively, I think most of us would probably say, no, there's something different about science than art. Maybe we can't put our finger on it, but I think most of us wouldn't go as far as Feyerabend. So if science is merely the product of the will of the scientist, the scientific community, and the cultural and historical location in which they exist, where does that leave us, if that's true, if Feyerabend is correct? Are scientific theories then arbitrary constructions? Or do they give a more or less accurate picture of the world as it exists apart from the human knower? So how much does science give us the world apart from human values and subjectivity? If science does give us an understanding of the world apart from human subjectivity, then can we say that science is talking about reality? Can we be realists about scientific theories? And can we say that science is progressing towards truth? Or do its theories merely prove useful to humans at a given time and place, given a particular set of interests? And so these are the sort of questions that philosophers of science are asking today. One philosopher of science I find quite interesting that I like, I'll say, so you're getting my bias here. There's a picture of Feyerabend, by the way, which looks very much like, his book Against Method. I think that picture sort of captures that. The other guy here is a guy named Amir Lakatos, and he argues for realism in science. He wants to get back to an idea of science actually saying something about reality, and he advocates what he calls sophisticated falsificationism. He agrees that falsification is seldom conclusive and occurs only over time. He also acknowledges that crucial experiments in science are recognizable only in hindsight. However, we shouldn't go with Thomas Kuhn, he says, and see the unit of science as the whole paradigm, but rather we should talk about what Lakatos refers to as research programs. So what does he mean by research programs? Well, according to Lakatos, a research program consists of a central core, which he says are a series of fundamental claims that essentially characterize any given scientific research program and guide future research. But in addition to these central claims and central core of a research program are what he calls auxiliary hypotheses. And these are less central concepts that surround the core as a protective belt which stabilizes the research program against the ocean of anomalies. A research program is progressive when it is able to predict unexpected facts that are later verified. And we can use Einstein as an example of a research program. So the recent finding that neutrinos go faster than the speed of light, right? They might not touch the central core of Einstein's research program of general relativity, but rather some implications of that central core. And so that is why Lakatosh would say people aren't just abandoning Einstein's theory all of a sudden because of one experiment. And that's sort of, Karl Popper's method would have scientists abandon a theory if one experiment seemed to prove it wrong. But Einstein, when he first started his research program in general relativity, and that's the general relativity refers to the large-scale structure of the cosmos, he predicted several things that would happen if he was right and Isaac Newton was wrong. One of those things was something called gravitational lensing, and that's the effect of what would be called a gravitational field on the trajectory of light. And this was something that he predicted several years before photos of a solar eclipse proved that this was in fact happening. And so Einstein's theory made lots of predictions that have been found to come true, and that's why we would say it's still a progressive research program. There are also what are called degenerative research programs, and these are what happens when a given research program strains to make the evidence fit with its central core. When research programs start making up ad hoc explanations, when they start changing their fundamental convictions, when they start sort of making their theory fit with the data rather than making novel predictions. And I have here an example of young Earth creationism, just because of the sentence here. Here's the conclusion, what facts can we find to support it? If that's your approach, then you're in a degenerative research program. If you're looking to see what facts can support your conclusion, in the sense that you're trying to change the facts in essence. It doesn't fit perfectly, but it's the best I could find for a degenerative research program. But the research program approach of Lakatos admits that there are ambiguities in scientific decision-making, that everything isn't perfectly rational. It also allows, though, a key place for the rational evaluation between rival theories, that you actually can look at two theories and you can decide between them, as opposed to quickly moving, sort of religious conversion in a drastic way from one paradigm to the next, as Thomas Kuhn said. Science doesn't always happen like that. People do decide between rival research programs. It also allows for progress in science and a sort of truth in science as unsuccessful research programs are rejected and as new data give credence to other research programs. So what we have then are some basic components of science. The first is data. We have collections of information about physical processes that are gained through observations of the natural world. And then we have theories as a second component of science. And these are empirical generalizations of data and conceptual constructions which explain why the data exist. But beyond that, we have this thing called shaping principles. And this is where it gets interesting as we talk about the dialogue between the Christian faith in science or theology in science. A lot of this conversation is in the area of shaping principles, which have been agreed by everyone to be a key component of science. And these are non-empirical factors and assumptions that are both current and historical that form the basis of science and go into selecting a good theory. These sort of shaping principles are as key to science as theories and data, right? But often when your average person thinks about science, they tend to get rid of shaping principles. They think, well, science is absolutely objective, absolutely neutral, absolutely value-free. There's no, history is unimportant to science, things like that. And that's just not true to the actual practice of science. So if we were to think logically about science, I would argue that we would accept these insights, the sort of insights that we talked about today, especially on the last slide, and the conclusions, which I'll talk about in a minute. And these are the insights accepted by the consensus of philosophers of science. Beyond the questions of debate, these are the sort of things that everyone accepts. Everyone accepts that the received view, the view of Karl Popper, is no longer the best description of science. It's really not how science happens, and it's not how science should happen. We should expect science to be like that. One of the problems is, however, that many practicing scientists still understand science very much like the received view. And so many individuals who actually practice science, they do their everyday work, and a lot of them, I had a sister-in-law who, she's a research chemist, and she insisted that science was absolutely objective and value-free, and sort of, we'd have lots of interesting arguments, but she, I found many people to fit that mold. To not really accept the idea that there are shaping principles in science. So some conclusions there. Science is not purely objective. What do I mean by that? I mean, such notions as value-free science, pure observations, and conclusive falsifications of scientific theories should be rejected as myths of the past. There is no such thing as value-free science. Instead, there is an important element of holism in scientific practice, and there is an element of the subjective in scientific practice. However, that does not mean that science becomes completely relative in such a way that anything goes. And this is sort of the postmodern critique of science, that science is no different from art or poetry. That is not the case in science. Theories do not create their own supporting data. There are data that support theories, certain theories, and not other theories. So something definitely is happening there where scientific theories that are good are corresponding to something that is out there rather than something in the scientist's own head. It's also possible to test scientific theories and to refute them. But while strict falsification has turned out to be a red herring, you can't absolutely falsify any given theory. The core of scientific rationality is still centered around falsification, that we can formulate hypotheses that are subject to testing, and we can show some of these hypotheses to be wrong. Another conclusion. It is problematic to speak directly or confidently of the truth of our current scientific theories, right? We can't say that any given scientific theory is absolutely true and verified. And this has to do with the switch from inductive theories of scientific truth and ideas based on verifying or confirming science to ideas of falsification, right? And so, if we were to say the highest truth status we can attribute to any scientific theory or law, according to current understandings of science, we can say that it's not yet falsified despite our best efforts. And so that's really where we're at with science. That's the conclusions. That's just to lay it all out there.